Absolute continuity. This is the new topic. The definition is: a real valued function f defined on closed interval ab is said to be absolutely continuous on closed interval ab. Real valued function means the function giving the real values, right? So a real valued function f defined on the closed interval ab is said to be absolutely continuous on this interval if given epsilon positive, there exists delta positive such that the summation I going from 1 to n on the mod of f of xi dash minus f of xi is strictly less than epsilon. For every finite collection xi dash of non-overlapping intervals. Non-overlapping interval means they are not sharing the common points, right? With the condition that summation I going from 1 to n on the difference of this xi dash minus xi, this should be less than delta. And is the remark that an absolute continuous function is continuous and every indefinite integral is absolutely continuous. These are the two remarks. Please remember this. Next is we are going to show the lemma. If f is absolutely continuous on closed interval ab, then it is of bounded variation on closed interval ab. How do we prove that this is the bounded variation? F is of bounded variation. How to prove that? If the total variation for closed interval ab is finite, then we say that function is of bounded variation. So we need to show that this total variation is finite. Okay, let's move on to the proof. Now what is given to us that f is absolutely continuous on closed interval ab. This is given to us, right? This is given to us. Now let's take delta to be in the definition of absolute continuity. Let delta in the definition of absolute continuity, and for this I am taking the epsilon to be equal to 1, which corresponds epsilon to be equal to 1. Then we have to take the subdivision of this closed interval ab, right, for absolute continuity. So then any subdivision of closed interval ab, this can be split by inserting the fresh division points into the intervals, and the number of intervals, let's say this to be equal to k. Now each interval is of having the length less than delta, right? And here I am taking this number of intervals k, which is the largest integer, and its value is strictly less than 1 plus b minus a. This is the end points, the difference of the end points. So this k is strictly less than 1 plus b minus a divided by delta, right? So let's first write this. For this subdivision we define the total variation. So let's first write this. Then any subdivision of closed interval ab can be split into k set of intervals, and the length of each interval strictly less than delta, where k is the largest integer and this k is strictly less than 1 plus b minus a divided by delta. So for this subdivision of closed interval ab, we define small t, the total variation, to be equal to the summation on the mod of f of xi minus f of xi minus 1. Now this complete sum, what is this complete sum? less than equal to k. K is the largest integer, which is further strictly less than 1 plus b minus a divided by L delta. And k is the largest integer, which is strictly less than 1 plus b minus a by delta, which is finite. So when taking the supremum over all the possible subdivisions of the closed interval AB, we get this t is changed into capital T, which is less than equal to k, and k is finite. So we get that this total variation is finite. And when the total variation is finite, that means the function is of bounded variation. The function f is of bounded variation on closed interval AB. Right? Okay. Next is a corollary. If f is absolutely continuous, then f has a derivative almost everywhere. For this also we have to show that first that f is of bounded variation. And when f is of bounded variation, then we say that f has a derivative almost everywhere. So let's show that first f is of bounded variation. For that, again we take let delta in the definition of absolute continuity. The proof will be the same, which corresponds to, let's take the value of epsilon to be equal to 1. For this value, then any subdivision of closed interval AB can be split into the intervals, k set of intervals, and the length of each interval is strictly less than delta, where k is the largest integer. We are taking k to be the largest integer, which is strictly less than 1 plus b minus a divided by delta. For any subdivision of closed interval AB, we have the small t to be equal to the summation on the mod of f of xi minus f of xi minus 1. This sum is strictly less than k, where k is the largest integer less than 1 plus b minus a by delta, which is finite. So this is finite. And now taking the supremum over all the possible subdivisions of closed interval AB. So when taking the supremum, this small t will be changed into capital T, which is less than equal to k, and this is finite, so t is finite. So therefore, because t is finite, f is of bounded variation. On closed interval AB. And when f is of bounded variation, we say that hence f has a derivative almost everywhere. A dot E dot means almost everywhere, right? Okay, thank you. Stay blessed.